All right, so then if we take a look at number 5, BH3, you can see it has a difference of 0.1. And again, technically anything other than a 0 would be considered polar. But again, we're giving ourselves the benefit of the doubt. Up to 0.4 would be acceptable as nonpolar. So yeah, this is definitely a nonpolar bond. And even if we did say it was polar, they'd all cancel out anyways in giving us a nonpolar. Now, sometimes it's hard for people to see why these arrows would cancel out. So even though 0.1 is considered nonpolar, let's just say, well, technically it is polar. So the H is going to pull those electrons more. So let's say we wanted to look at it in like the extreme case. Okay, you might have a hard time seeing why these arrows cancel out. Well, we can kind of go ahead and figure this out. Let's say this is pulling up with a strength of 1, this one's pulling down with the strength of 1, and this one's pulling down with the strength of 1. Because the left and the right arrows going down aren't going fully down or fully to the left and the right, we'd have to break those up into vectors. And that's just a fancy way of saying you're going to break everything up into an X component and a Y component. So again, I'll let your physics teachers teach you more about that. But basically, this one's pulling fully up. And because this one's pulling down at an angle, it's not really pulling down with the force of 1 or left with the force of 1. So it's kind of an approximation there. So we could figure out what this force would be if we know what this angle is. And we can pretty easily figure out what that angle is. And this one's pulling down at an angle and right at an angle. So just to kind of help you visualize it, this left vector and this right vector cancel. And what do you think would happen to two little arrows going down and a big arrow going up? They're going to cancel. Again, if we wanted to take the time to prove it using sines and cosines, we could do that. But again, for right now, I think I'll just kind of pull the biology approach. Take my word for it, and if you want to learn more about those sines and cosines, I'll let your physics teacher explain that next year. Does that make sense? So even though they're not pulling across from each other, not pulling directly in opposite directions, something pulling a little bit down into the left, something pulling a little bit down into the right, and something fully pulling up will fully cancel each other out. So that's why the 5 basic domain shapes are usually considered symmetric. And all of those arrows, if they're equal, would all cancel out. Questions on that? A really good example of that would be number 6 here. So they do have polar bonds. That's a difference of 0.7. So it's pretty easy to see that this upward arrow is going to cancel the downward arrow. This arrow is pulling fully to the left. This arrow that's going back into the board at an angle, again, is kind of like saying you've got a little bit of an arrow to the right and a little bit of an arrow going back. This forward arrow is going a little bit to the right and a little bit out of the board. Once you break it up into those 90-degree angles, it's fairly easy to see. This arrow is going to cancel this arrow. These two little arrows mathematically will add up to this big arrow to the left. So they would all cancel as well. So again, this is one of those cool examples that you have a bond that is polar, but yet the overall molecule ends up being nonpolar. And again, maybe that's not something in science that you would have predicted. But when let's say you say that these have polar bonds, but when you go back to the lab and you actually have this chemical, phosphorus pentabromide, and it's for some reason acting like a nonpolar molecule, what do you have to do with your polarity theory? Do you just kind of brush it under the carpet and say, well, that's kind of weird? No, you got to change your theory. So then we address the theory. Well, why could you have polar bonds but end up acting nonpolar? We revise our theory to say, well, maybe these dipoles are canceling out. And sure enough, that's pretty much what's happening.
So are you gonna like ask like for the EN differences and molecular polarities? Like
Oh, totally, just like this. I'll give you, here's this molecule. Are the bonds polar or nonpolar? Is the molecule polar or nonpolar? Yep, so you'll just basically go through each step here. But again, you have to start with the correct Lewis dot structure, and you have to start with the correct molecular polarity, because there's a chance that even if the bonds are polar, if it's the right molecular shape, those arrows could cancel. Does that make sense? All right, and then last but not least, here's number 7. So this is kind of borderline ionic or polar covalent. So I think maybe yesterday, according to yesterday's cutoff values, this might have come up as being ionic. But again, there is no black and white line that says this is ionic and this is covalent. So if you just look at these elements, silicon is a metalloid, so that could kind of go either way. Is it more like a metal and a non-metal, or is it more like two non-metals? Well, why are we having such a hard time with this? Well, if you look at this value here, what's to say it's slightly ionic or extremely polar? Like, you're pretty much right on that line here. So either way, this is the picture you would get. The F is definitely going to pull the electrons more. Pulling up and down would cancel. Pulling back and front would cancel. Pulling front to the right, back to the left would also cancel. So that one's a little bit easier to see because all of those arrows are in equal and opposite directions. You don't have to break out any vectors for that. It's pretty easy to see how they all cancel. Any questions with that? So, quick show of fingers out of 7. How many of these polarity problems did you predict correctly? All right. Sweet. Good. Awesome. Any questions I can answer? All right, the last topic for the unit then would be intermolecular forces. This would be a good time for a stretch break. And then we'll get back to it on slide. Get that for you in just a second here. Slide 36. All right, and we're going back to our seats. So, real quick conversation with your small group members. We're going to be talking about intermolecular forces. That's a huge topic in chemistry, how molecules behave the way they do. So, anytime you're introduced to a new word, sometimes it's easy just to break it down. What do the different parts mean? So, can you think of any other words that start out with the prefix inter? Based on those words and what they have in common, what do you think the word inter or the prefix inter means? And from that, what do you think intermolecular forces might be referring to? So, quick conversation in your small group. Again, I think this is slide 36.
Intergalactic.
What?
Yeah. I like the word.
It's the force that
Galactic.
All right, back to the whole group. What are some of these inter words? Internet.
Intergalactic.
Yeah.
Interfere.
intercept.
All right, and that's probably good enough. Interfere, intercept. Okay, so what do all these words have in common? They all start with inter, but according to their definitions, what is similar about them? So if you're international, where are you? Okay, maybe in more than one nation. Okay, which country are you inside? Oh, you're in different ones. Okay. Intercept. Somebody like a defensive back, or who's the person that covers the wide receiver?
The corner.
The corner. Okay. The corner has to get where in order to make that interception? Oh, in between. They have to get in between the receiver and the ball to make the interception. If you are going intergalactic travel, which galaxy are you in? Are you in both galaxies at the same time? Okay, you're traveling. Well, which galaxy are you in? You're in between the two galaxies. An interstate highway takes you where? In between states. It's not going to take you within Pennsylvania. It would take you between other states, like Route 81. Did you guys know the odd numbers go north and south and the even numbers go east and west?
Did you know that the Pennsylvania Turnpike for a very short amount of time was America's Autobahn?
I did not know that,
Yeah,
but it kind of makes sense.
Are you serious? They had no speed limit?
They had no speed limit.
That's awesome.
Interesting. Okay, so would you agree the word inter means between? If you are on the internet, are you on Warwick's network? No. Are you on Amazon's network? No, you're traveling between the two networks. Warwick has a server computer. Well, probably more than one. Amazon definitely has more than one server computer, but you're taking the internet between the two. You're traveling between the galaxies. You're traveling between the nations. You're, I don't know, interfering between two parties or two people. You're getting between the receiver and the ball. So inter definitely means between. So now that we know that, what do you think intermolecular forces or IM forces might refer to? Quick conversation.
Forces in between the two molecules. That's right.
Perfect. And I heard some good conversations out there. They would be forces of attraction between molecules, the stickiness between molecules. Think of anything that it has ever stuck. Glue, a gecko walking up a wall, tape, okay? Like right now, I can feel my hand dragging across the desk. I can feel my hand sticking to the desk as I move across there. That is all based on intermolecular forces.
Wow. So even those things that you throw and they're like a hand and they stick on a wall?
Like Velcro?
Huh?
Like Velcro?
No, it's like that slimy thing.
Oh yeah, like if you chuck like slime at a wall, why does it stick to the wall? Because of intermolecular forces. So Velcro would be mechanical sticking, like a hoop and a look, like a hoop and a hook. But intermolecular forces are kind of the molecular Velcro. What causes two molecules to stick? So it's definitely the attractive forces between molecules. It causes molecules to stick to other molecules. This is what causes a solid to be a solid. The molecules have to stick to each other. Even liquid molecules are sticking to each other. Because if they didn't stick, they wouldn't be a liquid anymore. They would turn to a gas. And that's one of our definitions of a gas. We'll get to that in about 2 units, the very last unit of the year. A gas, by definition, is a substance that has atoms or molecules that have no intermolecular forces. In other words, the particles are completely spread out, not sticking. So what turns a gas into a liquid or a solid? Intermolecular forces. You got to get those molecules to stick somehow. There's 3 types: dispersion forces, dipole forces, and hydrogen bonds. Those are the 3 main types. Are there other ones out there like ion dipole attraction? Sure, but we'll cover that in AP chemistry. So 3 main types. And I have almost 3 more slides to cover. What do you think are going to be on those 3 slides? Dispersion, dipole. Hey, wait, I've heard that word before. I've heard of a dipole. A dipole attraction must be an attraction between 2 dipoles, and hydrogen bonding probably has something to do with hydrogen. So we'll do the easiest one first, or the weakest one first. A dispersion force. Sometimes people call them London dispersion forces. Either would be acceptable. So quick conversation in your small groups. What does the word disperse mean? And if these forces disperse after they form, do you think they'd be strong or weak? Quick conversation.
That would be weaker. Oh,
All right, what does it mean to disperse? If a crowd forms and then disperses, what does that mean?
to break
They
apart.
scatter, they break apart, they fall apart. So, do you think that sounds like a really strong intermolecular force or a really weak intermolecular force? Thumbs up really strong, thumbs down really weak. If it forms and then breaks apart, falls apart. Strong or weak? Yeah, that would definitely be the weakest of the three forces. So it is a weak, temporary intermolecular force. It's like a crowd forms and then disappears. An attraction occurs and then falls apart. You get a new attraction and it falls apart. A new attraction and it falls apart. So again, there are very temporary attractions. We're talking a split of a split of a split of a split second attraction. Maybe even like a femtosecond or smaller. Now, why does this occur? Well, it occurs because you have a temporary dipole. Would you agree those little dotted arrows up there look like a dipole? Okay, it's an arrow with a positive end to it. But notice how it's dashed. Which atom pulls electrons more, H or C? Right, technically it would be the C, correct? But we pretty much defined H and C as what type of bond? 2.5, 2.1. Now, technically, there is some polarity here, but we basically said, no, this is so small, this is a non-polar bond. Would you draw a dipole arrow with a non-polar bond? No. But keep in mind, the stick between those two atoms, the H and the C, are connected by a stick. Is that really a stick? No, that's a bond. What is a bond? Two electrons being shared. Are electrons just frozen in place? No, they're constantly moving. That electron cloud is kind of wobbling. For a fraction of a fraction of a fraction of a fraction of a second, just by chance, could those electrons be just a little bit closer to the H? Yeah. Could that make the C partially positive for a split second? Yes. And just based on random odds, if these electrons are wobbling back and forth here, not that the C's pulling them more, I mean, it is just a little bit, but just because of random movement for a split second, could those electrons be closer to that C? Yes, which would make the H kind of positive. As soon as this happens, for a fraction of a fraction of a fraction of a second, what happens if you have a positive and a negative atom next to each other? Positive and a negative? They get a really temporary attraction. As soon as the electrons move, which is going to happen really quickly, that's gone. It disappears. It disperses. So you get this really weak attraction, and then it's gone. Weak attraction, gone. Weak attraction, gone. So it's constantly happening, but it's a super weak attraction. Questions on that?
Is it enough to actually do anything?
Oh, yeah, totally.
Okay.
Totally. So, for example, methane, CH4. At what temperature do you need to cool methane to get it to stick to other methane molecules? Normally, methane, natural gas, is a gas. But if you get it cold enough, the stickiness, this dispersion force, will be enough to get those molecules to condense and turn to a liquid. At what temperature does methane turn to a liquid? What's the boiling point of methane in degrees Celsius?
What was it, the melting point?
That would be going from a solid to a liquid. Let's go with boiling point.
Boiling point is negative 258.9.
Degrees Fahrenheit?
Yeah.
Oh, gag reflex. Let me hit that in Celsius.
Negative 161.6.
You have to get this all over 150 degrees below the freezing point of water just to get these gas molecules to stick and turn to a liquid. But if you get it that cold, you get liquid methane, liquid natural gas. So do they matter? Yes, because if they didn't occur, you would never have liquid methane. It would always be in the gas state. So at some point, when you get these molecules moving slow enough, these intermolecular forces can occur, and therefore, Grayson, can you put that away? I think I already reminded you of that. Again, I probably wouldn't say anything had you done all your homework. But again, that's not happening, so that's not happening. Capiche?
Yeah.
So put it away. Awesome, thank you. So this is going to happen at negative 161.6. Why? Because it's such a weak intermolecular force. Now, at what point does it really matter? Would you agree if you start getting a really big molecule, let's say C12, dodecane, C12H26. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm definitely not going to draw all the C's and H's. I'm taking some shortcuts here, correct? Structural formulas. That has C's and H's as well. Even though all of those atoms have weak dispersion forces, would you agree each one has a dispersion force? It's kind of like an ant. Can an ant really pick up that much?
No.
No, it can pick up a pebble. You get enough ants together, they can move an entire mountain. So that's the way I want you to think of these dispersion forces. Even though individual dispersion forces are weak, what if you put a lot of them together? What's the boiling point of dodecane? Do means 2, dec means 10. Dodecane would have a boiling point of what? Whoa, 216.2 degrees Celsius. What a difference. Again, it still has dispersion forces, but because it has so many of them, dodecane ends up being a really sticky molecule. You have to get it almost twice the boiling point of water to get it to turn from a liquid to a gas. So again, sometimes people walk away saying that dispersion forces are weak and don't mean anything. Well, that might be true if it's a really small molecule, but over a really large molecule, they really add up. All right, quick stretch break, and then we'll go over our last tip.
Allergies?
Why are you asking?
Well, not
All right, back as a whole group. 2 to go. Would you agree you've heard of a dipole before?
yes.
That would be an arrow in a polar bond.
Yes.
And if you have dipole-dipole, you must have 2 molecules that have dipoles.
Bi-dipole.
Okay? Oh, well, dipole-dipole. That's just what they call it, dipole-dipole. We're not very creative when it comes to naming things. If you got a dipole and another dipole, we'll call it dipole-dipole attractions. So this F, ooh, did I mess that up?
Yeah, it looks like the same exact thing.
Yeah, that F should be the negative one. I'll have to flip that arrow. Yeah, F definitely pulls the electrons more. So F is what, 4.0? And what is S? 2.5? Yeah, so F should definitely be pulling those electrons more. There we go. So F is definitely pulling those electrons more. So same picture, just I have my arrows flipped. I'll fix that. Would you agree the F is always going to be the negative end of that bond? And S will always be the positive end of that bond. Again, we're not even talking about a temporary dipole anymore. It is a true 100% there all the time dipole. So you need a dipole and a dipole. Opposite charges attract. This is going to be a much stronger attraction because it's always present. So it's like a dispersion force, except it doesn't disperse. It's always present. Those 2 molecules will always stick to each other. Questions? So positive end will stick to the negative end. Why? Opposite charges do what? Attract. Whose law says that? Coulomb's law. Again, it pretty much always boils down to Coulomb's law in chemistry. All right, now I should be able to sleep better. There we go. So yeah, F is definitely pulling the electrons. So it is a strong, permanent intermolecular force between polar molecules. For that reason, it's going to be a lot stronger attraction. So molecules that can experience dipole-dipole forces, are they going to have higher boiling points or lower boiling points? Higher melting points, lower melting points. Quick conversation in your small group.
Higher.
All right, molecules with dipole-dipole forces. Higher melting points and boiling points, lower melting points and boiling points. Yeah, definitely higher melting points and boiling points. Take a look real quick at what is the, we could probably come up with a molecule real quick. What is sulfur difluoride? Look up the boiling point for sulfur difluoride. SF2. SF2.
SF2?
Yep.
It is 39 degrees Celsius.
Oh.
Yeah, I didn't make you guys that time.
Thank you. Appreciate that. So methane, what is it? It boils at what, negative 160?
No.
All it takes is a little dipole-dipole attraction, and now it's going to be a lot stickier. Let's move on to the last one, H2O. That's about the same size as that, right? H2O, two H's and an O. It's the same molecular shape. What is the boiling point of water? It's 100 degrees Celsius. Well, how can it be so hot? Water is such a tiny little molecule. Why would it take so much energy to rip water molecules apart from each other? Because they're polar, which means they do have dipole-dipole attractions, but there's got to be another type of attraction that can fully explain this. You guys remember talking about hydrogen bonding in biology class?
Yeah.
There you go. Hydrogen bonding. Sitting around the campfire, singing some songs, roasting some marshmallows. Good old hydrogen bonding. Is that what we're talking about?
Fortunately, no.
No. So, what is a hydrogen bond? Would you agree it looks like a dipole-dipole attraction? It is. It's stronger. So, it's a special type of dipole-dipole attraction. Ooh, did I mess that up again?
Yeah.
What's the electronegativity of N?
3.
Yeah, I'm not sure why all my arrows got flip-flopped. Let me just fix that. All right, I can live with that. So what is a hydrogen bond? Obviously, it has hydrogen in it. Can everything with hydrogen bond? No. So it's a special type of intermolecular force. It's like a dipole-dipole attraction, but it's not a bond. It's still an intermolecular force. So H and N here have a bond. Okay, that is a bond. H and N are bonded together. This attraction between molecules that have H in them and 3 other atoms, that is a hydrogen bond. Now, really it should be called a super strong intermolecular hydrogen force, but they didn't want to call it that, so they called it a hydrogen bond. But it's not really a bond. It only happens in 3 cases. A molecule would need an HF bond, an HN bond, or an HO bond. And the way I remember it is, well, enough said about hydrogen bonding. Those are the only 3 cases. If you have H's bonded to C's, I don't care that there's hydrogen present, it cannot hydrogen bond. It has to be an HN, an HO, or an HF bond. NO or F. Another way to remember it, maybe slightly more controversial. If a chemistry teacher asks their students, is a hydrogen bond a bond? Their students should say what?
Yeah.
Is a hydrogen bond really a bond?
Oh, no.
No, but what their chemistry teacher really wants them to say is F no. Right? Because
No.
F, N, and O are the only 3 cases of hydrogen bonding. And it's definitely not a bond. It's a really strong intermolecular force. So whether you remember I said enough about that, or F no, it's not a bond, it's just a hydrogen bond. A super strong intermolecular dipole-dipole attraction between HN, FH, or OH. All right, now why is this the case? N, O, and F are the highest electronegative atoms on the periodic table. They're really pulling those electrons. So that's going to make the the N, O, and F super negative. That's going to make the H super positive. And what does Coulomb's law say about more negatives and more positives? They're going to be more strongly attracted. So again, it's just a really special dipole-dipole attraction that only happens in these 3 cases. Also, N, F, and O oftentimes have little lone pairs of electrons on them. Well, those electrons are negative, so that's going to increase the attraction between a super positive H. And because N, F, and O are really small atoms, the attractions can get really close together. What does Coulomb's law say about opposite attractions that are really close together? They're really strongly attracted. So for all 3 rules and reasons about Coulomb's law, this is a super, super, super strong dipole-dipole attraction. But again, it only happens 3 times. HF, HN, and HO. Questions about that? That right there is our unit. That was the last topic we needed to cover. Now, the lab would have really taken a look at this. We'd look at molecules that have HOs in them. We'd look at some molecules that have HNs in them. We'd look at dipole-dipole versus hydrogen bonding. But if you understand those 4 definitions, the 3 types and what an intermolecular force is, you really have all the concepts from this unit. So with that being said, we're going to review tomorrow. There's a Moodle review activity on Moodle. We can either do that all together, kind of as a big group, or we can kind of break up in small groups tomorrow. Do that. You can practice Quizlet. One of your options tomorrow will be to practice Quizlet, or if you practice Quizlet tonight and you want to take the optional vocab test in class tomorrow as part of your review, you can do that. So I'll give you 3 or 4 options tomorrow, but then the test will be on Thursday. Any questions? All right, again, that is the unit in a nutshell. We are skipping the Polarity lab. It was one of my favorite labs. We just don't have time for it. But again, if you feel cheated out of that experience, you can do it virtually using Moodle videos, and you can still take that lab quiz if you want to boost your grade. So that's an option.